All right, students, we are looking at kind of the last thing with waves here. This is for physics class. We've been talking about waves, and I introduced you a little bit to some things with waves, like what a mechanical wave is. And I also introduced you to what an electromagnetic wave was. And we looked at that whole electromagnetic spectrum a little bit. Some other things that we've learned is a little bit about amplitude, frequency, and wavelength. What a transverse and longitudinal wave are. And then the last thing we did was we talked about the speed of a wave. So today, what I'm looking to get into is review a little bit and maybe help you understand how those terms apply to the two categories, electromagnetic and mechanical. And then also, we're just going to talk about wave interactions, like how one wave interacts with another wave. So, I'm going to start with a mechanical wave. A mechanical wave can both be transverse or longitudinal. And when we say transverse and longitudinal, that goes back to this slide right here, where it can be transverse or longitudinal. And a great example of that is sound. Okay? Because it's a mechanical wave, they have to have a medium required. There has to be a medium. For comparison purposes, if you were to look at an electromagnetic wave, electromagnetic waves can only be transverse. There's no such thing as a longitudinal or a compressional electromagnetic wave. But with an electromagnetic wave, a great example of that is light. And for a medium required, that would be no. So if you put some type of material in the path of light, it's going to stop it. Whereas if you put some type of material in the path of sound, it usually improves the conduction of sound, because sound right now is traveling through a gas and it travels through a liquid and a solid much better. So if I wanted to show you a simulation that talks about kind of sound, this is just a wave simulation where if I wanted to review some of the terms, some of the things that we've learned, I can turn this little water tank on its side and we can see things like, you can see the amplitude. So if I wanted to pause this and we could reference where a normal line, this is a crest, this is a trough. We could measure the wavelength by taking the little tape measure here and going from the tippy top of one wave to the tippy top of the next wave. We could measure the wavelength. And then we could do things like, just so you remember, if you decrease the amplitude, that means that the waves are going to get smaller. So now they're not even touching where my tape measure is because they're smaller. And if I increase the amplitude, now they're going to go over where my tape measure was because, well, maybe not. Looks like they're right at the same spot they were, so maybe the amplitude was already at its max. But you can remember, amplitude is how strong the wave is. The frequency measures how many there are, how many waves you see on the screen. So if the frequency increases, that means that the wavelength is going to decrease. So there you go, I increased the frequency, there's way more waves on the screen now, and the wavelength is going to decrease. So if I put my tape measure without changing anything, not even close to what it was before. So when the frequency goes up, the wavelength goes down. When the frequency goes down, the wavelength goes up. Let's talk a little bit about sound. In terms of a wave, I'm going to play the sound here. I actually want to hear what it is, because with sound, if we're talking about sound, going back to my notes, remember sound requires a medium. Light does not require a medium. So I could actually click on particles here, and this is how the air particles move with sound. Sound is a compressional wave, so if I pause this, you can see an area where the particles are compressed together. That's called the compression. And then an area where it's thinned out, that's the rarefaction. An area of compression, rarefaction. Light, on the other hand, notice there's no option for particles here. Because if you put particles in the way of light, it stops them. They don't get compressed or spread out when light hits it. It just stops. So, going back to sound, play my tone. I kind of like looking at it in this pattern a little bit better. Once again, if I'm comparing sound here, I can go back to my notes. The amplitude in this case is the volume. Amplitude is volume. So, there it is. Hopefully you can hear that. Frequency for sound is the pitch or the note. The frequency is the pitch or the note. So and then lastly, the speed of the wave, it depends on what the medium is. If we were to turn that annoying sound off and look at light on the other hand, there we go, I'll flip over to light and I can turn my light on. You can see what the light looks like. It's moving out in all directions from that pulse right there. And if I wanted to look at light, first thing, the amplitude for light refers to how bright it is. So if I change the amplitude, you should notice a difference in how bright the light is. And if I make the amplitude go all the way down to 0, well, then there's no light being emitted at all. And if I increase the amplitude a little bit, you'll see that it's kind of a real dull green. And if I go up to all the way to the max, you'll see it's a real bright green. So amplitude determines how bright the light is. The frequency in this case controls the color of the light. So frequency, if I change the frequency, if I increase the frequency, you get kind of this purple color. And if I decrease the frequency, you'll get red. And I don't know if you remember this, but you get the whole Roy G. Biv thing. Red, orange, yellow, red, orange, yellow, green, blue, indigo, and violet. Those are my frequencies for light. And then lastly on my chart, what you have is you have the speed of light. The speed of all electromagnetic waves will always be the same. It's always going to be 3.0. Always going to be 3.0. It's never going to stop. So let's get into interference a little bit. Interference is how two waves can interact with each other. And if you have two different waves that are traveling towards one another, there is going to be an interaction between them. So what I mean by that is, if I had two waves, so here you go, here are two waves, there's the red wave and the blue wave, and I can make those waves move towards one another. And when those two waves move towards one another, they're going to do something to interact with one another. So for example, right when they start to touch, the two waves start to do something, and you can see that this purple line is the result of how they're interacting. So there's two ways that we describe how waves interact. We call it constructive interference. We call it constructive interference and destructive interference. So I first want to talk to you a little bit about what constructive interference looks like, and I'm going to put that right underneath that sign. Feel free to write these down as notes. Pause the video right now. Write down what constructive interference is. It's when, here's an example of it, for constructive interference. If the two crests line up perfectly, and the two troughs line up perfectly, and then the two crests, two troughs, two crests, and so on, what you get is you get the wave becoming stronger, becoming bigger. The wave seems to add to itself, so some people call this addition when they're talking about it, or amplification would be another term for it. I'm going to bring this one back, and I already have it checkmarked where we're looking at constructive interference. So when these two waves come together, when this trough interacts with this trough and this crest interacts with this crest, notice what happens to the overall wave. You get constructive interference. Now I think it's a little bit hard to see when you have the two waves be exactly the same size. So what I'm going to do is I'm going to pull them back apart, and I'm going to make one of them bigger than the other one, and then you can kind of see what I mean when I say that we're adding them together. So if these two waves go together right where the two crests and the two troughs line up. So here's the red one, here's the blue one. The purple line would be the resulting wave. So it's almost like if you take this distance right here, whatever that is, and add it to the top of this. You're taking, like if this is 5 and this is 10, there's no numbers on this chart or this graph, but if we're just making them up, if this is 5 and this is 10, then the purple line would be 15. You just add them together. And that's what constructive interference does. It's an addition of the two waves. You put them together and you get one resulting wave that's much bigger than the other ones. Another way to talk about wave interaction is to talk about cancellation or destructive interference. So if this is constructive interference, I'm going to put that one away. Hopefully you had enough time to write that down. Here is destructive interference. And destructive interference is where you have a subtraction of the two waves. It's where a crest meets a trough. And when a crest meets a trough, they almost seem to like subtract from one another or cancel each other out. Again, I'm going to go back to this little simulation that I have right here and click on the destructive button. And in this case, if you notice, what we do is we have a crest that's going to line up with the trough. And we have the crest here that's going to line up with the trough. So when those two waves come together and they line up perfectly, where the crest is over the trough, you get destructive interference. And again, if one of them was bigger than the other one, like if I go and I make this the blue one bigger, it's still the same thing. You're going to have a subtraction of the waves. So in this case, they're not going to cancel each other out perfectly because they're not the same size waves. But when they get together, the resulting wave is a subtraction of the two. So if this is 10 and this is -5, well, the result is going to be a wave that's got an amplitude of 5. Because this was positive 10, this is -5, so you'd subtract those two numbers. 10 minus 5 gives you an amplitude of 5. So it would, like if we're talking about a sound wave, destructive interference would be, it would sound softer, it would sound not as loud. If you're talking about light, this light would be not as bright if the two light waves were canceling each other out. So that's a little bit about destructive interference, and I got a whole page of things where we can look at interference and what happens when two waves move towards one another. What happens to the overall example. And I don't want to spend a lot of time going through these because there's some other really cool demonstrations. But you can slow it way down here and you can see what happens. So this is obviously a case where right now we're seeing constructive interference because the two waves are adding together. And if we focus on this blue one and this red one, we're going to get a moment where the crest and the trough line up. And when the crest and the trough, look at it's destructive interference through that whole part where they're lining up. And then the waves are going to separate and just move away at their normal speed. And I can choose different waves. So I've done that right here. I actually have a couple of different waves, and I'm going to have these go together real slow like this. And again, watch what happens when a crest meets a crest. You're going to get constructive interference. So here we go. Crest meets crest. And when that happens, you're going to get constructive interference, and then destructive interference, and then constructive interference, and destructive interference, and then constructive interference. And if I can get them lined up, ooh, that was perfect. I did not mean to do that really well, but here the red crest is with the blue trough, destructive interference. Blue crest is with the red trough, destructive interference. And if we let it keep going nice and slow, if I try to pause it in the exact opposite scenario, when the two crests are together, that's when you get the addition scenario. I also have some other, I'm going to go back to that PhET simulation where I had the light before, because this works out kind of nice to show you interference. And I can just show you interference with a couple of water waves. I'm going to switch back over to the top view, and I can get more than one water wave going at a time. And when I get more than one water wave going at a time, we get this interference pattern that shows up. And I'm going to talk about this one a little bit later, but I do want to show you sound. I'm going to turn the particles off and only focus on the waves for sound. So I'm not going to play the tone because it's just kind of annoying to have to talk over it and stuff. But this is an interference pattern that happens, like let's say you're at a rock concert. And if you're at a rock concert and you have two sets of speakers, a speaker on the left side of the stage and a speaker on the right side of the stage, and the band's playing the music, this is what the audience would hear. Now, I'm not sure if you can really see this pattern really super well, but what you get is you get these areas where there's constructive and destructive interference. And if you were sitting in a seat right in this area right here, the sound would be pretty uniform for you. You would hear because the sound waves are moving so fast, you're not going to hear the highs and the low parts of that. But here's the important part. Look at this line right here. And if you were sitting in this line right here, the concert or the venue, it would sound really bad because you're not getting any real sort of wave. This is an area where it's always being destroyed. This is destructive interference. Let me pause this for a second. These areas right here, the sound for the show would be really bad. Anywhere where those are. And I can move my slits so that they're closer together or further apart of my speakers. And this is part of why they kind of build the venues the way that they do. Again, you can kind of see those areas now. And look at how much bigger they are when the speakers are close together. This is an area you would not want to be at a concert. It would sound really bad. And same thing. So speaker placement at those concerts is critical. They have to put them in places where it just makes sense. And typically you'll see when you go to a concert that they put the speakers as far apart as they can because they're minimizing the number of seats that are affected by this. Some venues actually arrange the seats so that this is an aisle where people walk up and down. Like let's say you got to leave your seat's here, and you got to leave your seat to go to the bathroom. Might be a spot where people are walking as they're leaving to go down to the bathroom to do that. So the moral of the story is typically at like a rock concert or a rock show or something like that, you're going to see the speakers further apart so that the aisles themselves are a little bit smaller and you get a lot nicer sound when you're listening to it. This is the exact same thing. This is with something that's called a ripple tank. And if I hit go here, you'll see the kind of the same scenario. This was done with water. So you're actually seeing water right now. And you can see the same pattern that I was just talking about. Places where there's waves and where there's great sound. In this case, there's really cool waves here. And then you get these areas here where there aren't waves. Or they're in the case of a concert, this is where it would sound really, really, really bad if you were looking at a concert. Just for the record, if you're doing it with light instead of doing it with sound, you would get the same kind of an interference pattern. You have places where there's constructive interference and destructive interference, and then you have these areas, these dead zones, where it would be really dark. If you had two different light sources that were strobing like this, that's the pattern that you would get out of it. So it is the same exact thing with light. I want to talk about a different kind of a wave for just a moment, and it's something that's called a standing wave. And it happens to be a unique situation where constructive and destructive interference sets up perfectly. So a standing wave has a couple of special spots in it. So there you go. There's a standing wave for you. Ooh. And with a standing wave, you get this situation where it looks like the wave doesn't move anymore. So I know that that's really hard to picture what that might look like, which is why. So I moved my camera over, and you can't see it, but I got this kind of a neat toy thing going on right here. I'm going to go to a bigger screen so that hopefully we can see everything and that everything works out. There you go. And you can see my kind of a neat toy thing that I got. Normally when the wave moves, it moves to the left or to the right. So if I turn this on, it'll take it a second, but eventually it'll kind of even itself out here. There we go. And I'm going to try to make what's called a standing wave right in the middle of this. And it might take me a second to get it going. Oh, I'm pretty close. I'm going to try to get all that string off of there. Or just try to set it up one more time. See if we can't create a nice standing wave. I have not made one yet. So this is the joy of going live. Oh, there we go. Pretty darn good right there. So I got myself a standing wave. So the wave no longer looks like it's moving to the left or looking like it's moving to the right. It did just a minute ago. But right now it does not look like it's doing that. Instead it just looks like it's standing. And we have these places. This is a place right here where the crests or troughs are lining up. This is a place where the crests and troughs are lining up. And this is a place where the crests and troughs are lining up. We have names for these areas. And here's a spot right here where it's 100% completely destructive interference. And here's a spot right here. I can put my finger in there where it's 100% destructive interference. Look at that. It's just focused right there. It's not even moving. It's just staying completely isolated right there. So if I went back to my notes, I wonder if I can do that. I had to get out of the big screen. I'm trying to reach around my camera. You can see those spots that I was referencing. Here's one of them. This is a place where there's 100% constructive interference. And then right here, here's a spot where there's 100% destructive interference. Constructive, destructive, constructive, destructive, constructive, destructive. So we have names for those. A place where there's maximum amplitude constructive interference, that's called an antinode. So this is an antinode. This is an antinode. This is an antinode. In my picture right here, this is an antinode. This is an antinode. This is an antinode. And then we also have this area where a node is where there is 100% destructive interference. So this is a node. This is a node. And this is a node. I'm going to switch back over to the big camera display. And I'm going to hit pause for a moment because this toy is even better in the dark. I can control the lights and I can make them strobe and stuff and flash, and when you make them flash you can see stuff like that. It's pretty darn cool. I'm going to make it go a little bit slower. But right here, that's an antinode. That's a node. Antinode, node. And what do I want to do? I want to make it there. Oh, that is pretty cool on the camera. If I actually kind of go back and try to like recreate this again now, I like this pattern for the lights the best because I think it looks pretty cool. There we go. Oh, that's sweet. But I'm going to turn it off. Or actually, I'm just going to grab the string so that I don't have it as a standing wave anymore. This is now a wave. It's trying to set up that standing wave where it looks like the wave is moving around. It looks like it's moving to the left. It looks like it's moving to the right. And if I give it enough time, those areas where there was positive interference, constructive interference, are going to line up. And the places where there was destructive, I didn't touch anything. I just let it do that on its own. Now if I do touch stuff, I can move this arm over here. So like this little arm, I can move that. And when I move that, I can make it do, try to set up a wave again. And there you go. Constructive and destructive interference. I got one big antinode here, one node, one big antinode. And all I'm doing is moving these things closer together or further apart. There you go. I got all kinds of interference going on, all kinds of waves. This is not a standing wave at this point in time. I got waves going to the left, I got waves going to the right. They're interfering with each other. You're seeing those interference patterns. And I don't know, it's kind of a neat thing. And if I move these arms closer together, I can set this up to where I get my standing wave again. Oh, it's really close right there. It's getting close. Trying to find that standing wave. Close. This wave still looks like it's moving around a lot though. There it is. A standing wave. No longer looks like it's moving around. So hopefully by looking at this you get a pretty good idea of what I mean when I say a standing wave versus a regular. So I do have one more demonstration to set up, and it is, howdy, here I am. It's got all kinds of parts to it. Ooh, I dropped my camera, sorry about that. I got my pendulum clamp from school, and then I'm going to follow, there's a spring set up, and that spring comes down here to this wave generator, and I'm going to turn it on for a second. So the wave generator, it's just a machine, and it's making my spring vibrate. And I can control the frequency of the vibration. if I follow these wires down here to that machine, that's a frequency of 118. That's a frequency of 145. And what I can show you with that is I can show you, I'm going to try to set up a standing wave that's longitudinal. This is really hard to do, you guys, especially in a way that you can see it on that screen. So I'm going to try to get it. I'm just going to change the frequency. And by changing the frequency, I'm going to try to get a standing wave that I can see on the screen. And I'm going to pause the video for a second while I try to do that, because you guys can kind of see what I'm doing here now. I'm just changing the frequency, and eventually I'm going to get a standing wave set up, but it might take me a while, so I'm going to pause. I think I got it, and I think it looks pretty good on the camera. I have a spot where there's a compression right here, and then a rarefaction, and then a compression, and a rarefaction, and you can see them in the spring. It's better if you're alive. Oh, and I lost it. They're gone. So you can't see them on the camera anymore, but I had it there for a second. And I got it one more time. Right there, I have it right there. I have a compression and a rarefaction and a compression and a rarefaction